chocolate and peanut butter, two materials that don't naturally cooperate. One is cocoa butter based, brittle when cold, unstable if tempered incorrectly. The other is oil heavy, granular, and prone to separation. So how do you make them lock together at speed by the millions? Reese's started as a penny candy. Today it's a multi-billion-dollar manufacturing engine. The product looks simple until you try to produce it consistently, because every cup is a stack. Bottom shell, peanut core, top seal. If any layer drifts, the entire structure fails. Failure modes. Over-roast peanuts and bitterness dominates. Under-roast and the flavor tastes flat and raw. If peanut butter oil migrates, texture collapses. If chocolate temper drifts even slightly, fat bloom appears. White streaks, cracked shells, dull finish. At industrial scale, small mistakes don't make bad pieces. They make bad pallets. Signature moment. Today we're going inside the Reese's production line. From raw runner peanuts, to engineered peanut filling, to chocolate tempering, to the precise stacking sequence that creates the cup. Shell, plug, cap. Receiving peanuts controlled input. It begins with runner peanuts, the variety chosen for uniform size and high oil content. They arrive in massive super sacks, each weighing thousands of pounds. Forklifts hoist them above stainless steel hoppers. The bottoms release. Peanuts cascade down conveyors in controlled flow. But before flavor, before grinding, comes protection. Because one small stone inside a grinder doesn't just ruin flavor, it destroys machinery. Destoner, removing the hard problems. Peanuts pass across a vibrating destoner platform. The system separates materials by density and vibration. Peanuts move forward. Heavier debris, rocks, shells, metal fragments, shift backward and fall away. It's simple mechanical sorting. Clean input means stable output. Manufacturing begins with subtraction. Roasting, the Reese's flavor profile. Next, the tunnel roaster. Long chambers, controlled airflow, measured heat. Unlike lighter peanut butters, Reese's intentionally pushes the roast slightly deeper. Not burnt, but bold. The higher roast develops Maillard reactions that amplify nuttiness and introduce subtle caramel tones. The granular texture fans recognize isn't accidental, it's a roast-driven structure choice. Flavor here is engineered through time and temperature curves. Blanching, skin removal at speed. After roasting, peanuts enter a blancher. A rough surface conveyor agitates them. The papery skins loosen. Air jets pull the skins away. Removing skins prevents bitterness and ensures smoother grinding. Now the peanuts are hot, clean, and chemically primed, ready for transformation. Grinding steel plates, millimeters apart. Peanuts fall into industrial grinders. Inside, steel plates spin at high speed. Clearance between them measures just millimeters. The nuts fracture. Friction builds heat. Cell walls rupture. Natural oils release. Solid peanut becomes flowing paste. At this stage, temperature control matters. Too hot and oils degrade. Too cool and texture becomes uneven. The result? Fresh, warm peanut butter moving through stainless pipelines. Stabilization, stopping oil migration. Fresh peanut butter wants to separate. Oil rises, solids sink. For a jar on a shelf, that's acceptable. Inside a chocolate cup, it's a structural disaster. So stabilizers enter the formula. Small amounts of hydrogenated vegetable oil or emulsifiers bind fat molecules. Salt sharpens flavor. Sugar balances roast intensity. The goal isn't smooth spreadability, it's shape retention. Reese's peanut butter must hold geometry under pressure. Engineering the filling texture for the bite. Now the mixture becomes filling. Peanut butter is transferred into large mixers. Powdered sugar increases viscosity. Emulsifiers ensure homogeneity. Dextrose enhances roasted peanut perception and moderate sweetness curves. This formula is intentionally thicker than sandwich peanut butter. It must remain stable inside a chocolate shell. When you bite a Reese's cup, the filling doesn't ooze. It fractures softly. That bite texture is engineered. Chocolate production, structure before flavor. On a parallel line, chocolate is being prepared. Cocoa liquor, cocoa butter, sugar, milk solids, emulsifiers like lecithin. The mixture passes through refiners that reduce particle size below detectable grit levels, then into conching machines. Conching smooths texture and removes volatile acids. But smoothness alone isn't enough. Chocolate must be tempered. Tempering aligns cocoa butter crystals into a stable form, specifically form Vive crystals. Without tempering, chocolate sets dull, soft, and fragile. With tempering, it sets glossy and snaps clean. Structure first, flavor second. Paper liners. Precision before chocolate. Before chocolate even flows, paper liners are placed into molds. Machines drop them at high speed into recessed trays. Operators monitor for misfeeds. Double liners, tilted liners, missing liners. Because if the liner folds incorrectly, chocolate seeps. If chocolate seeps, packaging fails. And if packaging fails, product fails. Precision begins before pouring. Bottom layer, the base shot. Tempered chocolate fills a depositor above the line. Calibrated nozzles release measured volumes into each liner. The bottom layer spreads outward. Air pulses and gentle vibration lift chocolate slightly up the sides. This forms the shell wall. Wall thickness determines structural integrity. Too thin and it cracks. Too thick and it overwhelms the filling ratio. The base shot defines the cup. Peanut plug, the center drop. The filling line synchronizes above. An extruder pushes continuous ribbons of peanut filling through circular dies. Rotating blades slice perfect discs. Peanut plugs. Each plug drops precisely into the center of the chocolate base. Not too high, not off-center. Vibrating conveyors settle the filling gently. Proper settling ensures bonding with the top seal. Alignment here is everything. Top layer, the seal. Final step in stacking. Another measured chocolate pour, the top layer flows over the peanut plug. Air smoothing removes surface irregularities. Chocolate meets chocolate at the edges. Fusion occurs. Shell, core, seal. The Reese's cup is structurally complete. Cooling tunnel, locking in the snap. Fresh cups enter a cooling tunnel. Temperature gradually drops. Humidity is controlled. Cooling too quickly introduces stress fractures. Cooling too slowly risks deformation. The tunnel stabilizes cocoa butter crystals. This is where gloss is locked in, where snap is finalized, where structure becomes permanent. Once cooled, mechanical demolders lift cups from trays. They transfer onto conveyors in perfect rows. A separator wheel groups them into pairs. Because Reese's doesn't sell one, it sells two. That pairing is part of the identity. Wrapping plus logistics. Pairs slide into orange film. Heat seal jaws close, seams fuse. Wrappers trim clean. From there, automated cartoning, palletizing, refrigerated distribution. Because temperature stability continues after production, chocolate remains sensitive through transport. Product stability, the shelf life equation. Shelf life depends on fat stability and moisture control. Peanut oil must not migrate. Chocolate must resist bloom. Packaging limits oxygen exposure. Climate-controlled storage protects texture. Every stage extends viability without altering bite quality. Consistency isn't just a factory problem, it's a logistics problem. Why it works. The brilliance of Reese's isn't invention, it's control. Controlled roast, controlled grind, controlled temper, controlled stacking. Two unstable materials, engineered into one stable unit, millions of times per day, identical. Chocolate structure around a peanut butter core, shell, plug, cap, made by the millions. One identical cup at a time. Next, Dunkin' Donuts, where frying, proofing, and glaze timing decide the perfect ring. Inside the system.